I played the sax, but I wasn't playing the sax like that guy, the guy with the dreads when I was his age. They were amazing. Let's give it up to them. Yeah. Okay, so music has this mysterious power to affect us so deeply. And never in my wildest dream, when I started off in my career to become a physicist, did I ever think that there would be some deep connection between the functioning of our universe and music. And I want to take you a little bit on that journey today. The journey begins at DeWitt Clinton High School. This is where I went to high school in the Bronx, New York, in the 80s. And DeWitt Clinton was the second most populated high school in New York City, with about a 60% dropout rate. But we had teachers there that deeply cared about our well-being and our education. During 10th grade, our first day of our physics class, all of the students were anticipating Mr. Kaplan to walk into the room and walk to the front of the blackboard and write down some daunting equations. But he did the exact opposite. That's a picture of Mr. Kaplan when he was a younger chap. It was the only picture I was able to get, but the Kaplan at the time had wild Einsteinian haircut, and he walked into the room with a frail limp and actually went and sat in the middle of the room on someone's desk. And he reached into his inside pocket, actually one of the pockets, and to get some mysterious object that actually made the thugs in the back of the room a little bit concerned, okay? But it was just a simple tennis ball. And he took the tennis ball, looked around, threw it in the air, caught it. I'm glad I caught it. And then he asked the class, when the ball was at the top of its flight, it had 0 velocity. Right before it hit my hand, what was the velocity of the ball? Now, we were about 14, 15 years old at the time, and I was fascinated by this because I didn't have to solve any equations. In my mind's eye, I had the image of the ball going up and down in slow motion, and I instinctively rose my hand, and I said, well, when the ball gets right before it hits your hand, it's exactly the same velocity as when it left your hand. Mr. Kaplan got up and said, this is brilliant. The intuition is the lifeblood of a great physicist. I'm like, really, me? It was the first time, it was the first time in my life that a teacher actually, exuded that I was smart. After class, Mr. Kaplan called me into his office. So I went to his office, and he had this huge office, because he was the chairperson of both the music department and all the science departments. And it had all these books. There was a book, actually this was one of the books. It's about a 2,000-page book on gravitation. And he says to me, Stephon, I think you have what it takes to be a good physicist. I'm thinking, what? I haven't even had one class with this guy yet. I'm like, one class? What's he talking about? And he goes, yeah, do you know about Einstein's theory of gravity? Space is not what you think it is. Space is warped. The universe is expanding. And he goes, what kind of music do you like to listen to? So because in his office, he had on one side of his office a picture of Albert Einstein, and on the other side of the office, he had a picture of somebody I didn't know. Although I did play around with a saxophone when I was younger, I actually didn't know who this gentleman was. It was John Coltrane, of course. And of course, I wondered, why does this man have these two people in his office? I know about Einstein, but anyway, to make a long story short, he basically told me, hey, what kind of music do you like? I said, I like rap music. He said, what about jazz? I said, I like Kenny G. So he said, come back to my office next time. I came back, and he handed me a CD. He goes, this is real jazz. And it was a John Coltrane's album, Giant Steps. All right, the years progressed along. I discovered something very interesting about Mr. Kaplan. Mr. Kaplan was trained as a master composer, and he was on his way to a very successful career as a composer. But he got drafted in the Korean War, and during the Korean War, he got involved in radar. And while working on radar, he caught the physics bug, because radar is about physics, right? And when he came back, he pursued a career in physics and then became the head of the physics and music department pursuing both careers. He was also a jazz musician. But Mr. Kaplan could have taught at any of the elite schools, like including Browns High School of Science, which is next door to Clinton, but he chose to be right there in that room with me. So I caught the Kaplan bug. Mr. Kaplan said, you have to take calculus, you have to go to college, go to grad school, get a PhD, and then you can learn, you can understand this book. Well, I did that. It took 20 years to do that. So fast forward 20 years, I am in London at the Imperial College, the theoretical physics group, and I start to feel like that 10th grader again. I start to feel completely, inadequate. There were all these other physicists there that I felt had a lot more than I had. And I was getting nowhere in my research. So in that moment of despair, I remembered Mr. Kaplan. I remembered Mr. Kaplan being true to himself, paving his own path, improvising his life. So I decided, you know what? If I'm gonna go out, I'm going out with my horn. So what I did was I started to hang out in the jazz clubs in Camden Town, London. During the summer times, I used to go to Smalls, and I would bring my physics papers, my research, and my calculations to the jazz clubs. So now I'm in these jazz clubs in the middle of the night, talking to the jazz musicians about my physics ideas. I used to tell them about, the expanding universe. They would give me weird looks. There was a time when a pianist was playing, and I looked at another horn player. I said, man, his playing is quite geometrical. And the guy goes, I don't know about geometrical, man. This stuff just sounds good. So that was the story. But one thing happened that was interesting. During that moment, I realized that I was starting to have intuitive leaps in the jazz clubs, sometimes irrational thoughts that would lead me to solve problems. Because many of us think that being a good scientist is about being rational and locking yourself behind in a room, calculating in a desk or in a lab with a lab coat. No, sometimes to get to the answer requires you to be irrational. And that's what was happening there. So that led me to solve a couple of problems and got me tenure at Dartmouth College. But now it turns out that I learned something very interesting, that I wasn't the first to do that. It actually turned out that at the very birth of astronomy, the very birth, going back to the Pythagoreans, 580, 540 BC, they actually thought at the birth of astronomy that the universe played a harmony. They call it harmony of the spheres. That all the planets were playing this harmony. And in the 1600s, the first astrophysicist, we've seen a picture of him here, Johannes Kepler, in order to come up with the 3 laws of planetary motion, of the elliptical motion of all the planets, Kepler actually went back to the Pythagorean thinking of a musical universe. And how he figured this out was very interesting. What we're seeing here is the sun and a planet going around an elliptical orbit. And at the perihelion, where the planet is closest to the sun, here's the sun, the planet is closest to the sun, he measured the velocity, or the velocity was actually measured. Furthest from the sun, he measured the velocity, and he took the ratios of those velocity and assigned a musical note to that ratio. And he did that for all the planets and came up with the scales. And through that musical thinking, he transported that into his equations. So the Kepler's 3 laws are still used to launch satellites into outer space and keep satellites in orbits and to still study the motion of planets today. They're still correct. So I was very inspired by that and said to myself, well, I guess I'm going to have to use musical thinking as part of my toolkit on top of the math and all the other stuff that I use. And I kept very interesting methods there. So now we're thinking about 2020. I want to tell you guys what the current research going on in my field is. So I'm gonna talk about 2 things and focus on one. I'm gonna tell you what the cutting-edge research is. So many of you heard about this idea called the Big Bang. This is actually Einstein's theory of gravity. predicts that in the presence of matter and energy, the space-time of the universe actually is going to expand. So what we're seeing from your left to the right, yes, your left to the right, is that region where you have this shiny white light. That region actually is a big mystery. We call that the Big Bang. We don't understand how it came about and what happened before. That's what I get paid to do. Thank you, taxpayers, for paying me to do these kind of things. But what we do understand well is what happened afterwards. So what we're seeing there are the red and blue, this red and blue area there. That is something called a cosmic microwave background radiation that's been measured way back, in the 60s, and that measurement has been confirmed up till today. That corresponds to the early universe as it's expanded, that was very hot and dense and filled with radiation energy. Nothing else, no planets, no stars, no galaxies. And as the universe continued to expand, it cooled, and that radiation coalesced to form the first stars and galaxies that we now inhabit. And we understand that physics very well, but we don't understand the Big Bang, what happened before the Big Bang. Another problem we don't understand very well are the laws of physics. We know that there are 4 forces of nature, and all of these forces have different strengths. What we're looking at here is a typical star like our sun, and at the center we see iron. Because of the immense pressure of the sun, the immense pressure forces thermonuclear fusion to transmute light elements into heavy elements. So a star is a region or a factory that produces elements, heavy elements, like carbon. If a star does not produce carbon, there would not be life as we know it, because we need carbon for our DNA. So the question is, it turns out if you tweak the laws of physics, these forces, the strengths, by a few %, a star could never make carbon. So it's like the universe is like a perfectly fine-tuned instrument, such that if it was any different, if those laws are any different, it would not produce the stuff necessary for life. A star is what produces the stuff. So we're really made up of stardust. I want to show you a picture here. You see that arrow is pointed at a star within a galaxy? And that star explodes into something called a supernova. It's brighter than the entire galaxy, even though a galaxy has on the order of hundreds of billions of stars in it. All right? And so that's a picture of a star right before it, and that blows out all of the elements. Okay, so here's something really interesting. The Big Bang, the idea of the Big Bang, physicists today are thinking that actually this fine-tuning could be solved if before the Big Bang there were many bangs, and there were many universes created in those bangs, and we just happen to be in the universe where the coupling constants, what we call the tunings of these primes, are exactly necessary for life, but the other universes have different laws. So we just hit the jackpot. Are you satisfied with that idea? Well, this idea is what people are now working on at some of the top institutions around the world. So I returned back to my musical thinking, and I said, well, what if, like Kepler, the universe was more than just harmony of the sphere? What if the universe was like a jazz solo? So in a jazz solo, as you heard these wonderful young people play, you need 2 things to happen. You need a rhythm section, and what usually happens is that this rhythm repeats itself like a cycle. And you have a harmony, and that harmonic structure repeats itself as well. And every time that repetition happens, the improviser, the soloist, gets to try different things, gets to improvise different ideas. So, what if the universe was like something like that? So instead of having one bang, the idea is that you have an infinite successions of bangs. The universe, our past universe, expanded, contracted into a bang, expanded and contracted again, and every time it did that, the universe had an opportunity to solo different laws of nature. So with this idea, because that's what physicists we do, we have an idea, as crazy as it is, And then we start putting some equations behind it. So we turn back to Mr. Einstein, we go back to his equations, and we find, me and my colleagues, that the equations actually work out to actually say that. So I'm going to now close with some inspiration from Mr. Kaplan. And as we're thinking about 2020, I want to say to Mr. Kaplan, you know, when I got my PhD, I went back to DeWitt Clinton High School to thank him. And I found out that he had not too long ago passed away from cancer. And that that little limb that he had was because he was actually suffering from a terminal illness. So I felt guilty. I dedicated my PhD dissertation for him, but I actually felt guilty that I never, over those years, I was so busy with my own life, I never got a chance to thank him. And that's why I'm here to kind of pass on the Kaplan meme, which is that Mr. Kaplan demonstrated the courage to be true to himself. He demonstrated the courage to think differently and not fall into the traditionalism of one's field. And he also challenged us to live a life full of improvisation. Because if the universe is improvising, why shouldn't we? Thank you.